So now that we've looked at stress and we've kind of defined the formula, let's look at the different kinds of stress. And there's two kinds I want you to be aware of. The first one is just normal stress. And it has a synonym, which you need to know for your vocabulary, right underneath it in parentheses, axial. Axial stress. But what normal stress is, or axial stress is just force that is perpendicular to your cross-sectional area. Cross-sectional area. Oops. Just dropped something. And I'm going to go ahead and write CSA for cross-sectional area for future reference. We don't have to write out that term every single time. What do y'all say? Cool. All right. Now let's say two people are trying to rip something in half. Let's draw two people, here and here. And it could be a rope, but if it's a rope, they can't push, right? But they can pull on almost anything. They could push or pull. Let's say they are pulling. One person's pulling this direction, one person's pulling this direction, and they're trying to rip it in half. To calculate the stress applied to this thing, if it was a board or something else and use some metal, we would look at the cross-sectional area. Now, from this view, it would just look like, it would just be 2D, right? And so I lost my prop, which was a wooden dowel. Here we go. You look at this wooden dowel or this wooden rod. It's just a circular wooden rod, which looks rectangular to us. The point is, from the side, if we turn it sideways, we cut it in half. We'll call this our cross-sectional area from here. We will redraw our cross-sectional area if we looked at it from the inside, and it would just look like a circle. I'm going to draw it kind of like an oval just to show you. One force is going this way through our area, and the other one is going that way. And so it's kind of a diagonal view of the cross-sectional area. But the point is, there's the cross-sectional area. I turn it sideways. I look inside. Right? So when we say perpendicular, what are we talking about? Well, we mean this force is perpendicular to this cross-sectional area. The cross-sectional area, let's use this, is this way. Our forces are either pushing in or pulling apart, which is a perpendicular direction to our cross-sectional area. You can see right now that would be coming up, in this case, or going down, which is perpendicular to this flat surface. That's what they mean, just so we're clear. And let's go ahead and differentiate that with the other type of stress I need you to know about, which is shear stress. Put this back in black. Shear stress, on the other hand, and actually let's go ahead and put in parentheses the symbol for shear stress, which is tau. I'm sorry, that's a T. The Greek letter tau, like this. Looks like a backwards J. And that is force is applied parallel. And you might have heard the term shear before, to CSA. Has anybody ever heard the term shear before? Where? Interesting. Okay, anybody else? Sometimes scissors are called shears, right? Sometimes you shear, when you're cutting bushes. It's all kind of the same idea, and now's a good time to tape in our tape-in shear stress examples. Tape it off to the right. If you tape it off to the left, that's fine. You just got to draw everything I draw on the left off to the right. But these are all good examples, while you're taping this in, pay attention, of shear stress. So, for example, in this pretty picture right here on the top left, you've got two objects glued together and they're being pulled apart. Whereas these two objects, maybe it's like your bridges that you built, where you can see one board is pulling on this bolt or this screw one way, while another board is pulling on it the other way. And when you stand on your bridges, that's the direction it would pull, right? And then this one is doing the exact same thing. You've got this hinge joint connected. You can see how it's pulling into the cross-sectional area. You see how these are all kind of doing the same thing? They're not crushing our shape. They're not ripping apart our shape in half. Rather, pushing into it in opposite directions. Let's draw another example. I like to use, let me make sure I cross that out very well, because that's something I don't want you to worry about that you have to draw. That's not some Greek letter. I want to draw a pair of scissors. So, quick pair of scissors here, with two little circles there, make it look good. Let's put inside these little shears. Let's put a wooden rod, like the one I showed you. Like a little 1/8 inch wooden rod. And let's say we're trying to cut it in half. So what does that look like? Okay, we take our scissors and we're trying to cut it in half. This would be an example of shear. Now, I think everybody in here could do it with a pair of scissors, right? If you put enough force on it or enough stress on it. Right? All right, but here's basically what would be happening. Is let's look at this side view again. Let's draw a quick rectangle for ourselves. Looking at this side view. And we've got our cross-sectional area here. Let's call it CSA right here in this location. What would happen is we'd have one force pushing up one side of the scissors, pushing up across that cross-sectional area, and another side of your scissors pushing down, right? And what are we trying to accomplish? What we're trying to accomplish is one side going up literally, and another side going down literally, right? And so here's your cross-sectional area where you're literally trying to break this apart parallel to your cross-sectional area. And I think I've said literally enough times, but this is our cross-sectional area here, the same wooden dowel. We have one force going up, pushing it apart, and another force going down. So what I mean by parallel, I mean the force is going in line with our cross-sectional area. Does everybody get the idea behind shear stress and the difference between it and normal stress?